Welcome back to the Deep Dive. Today we're getting into the engine room of AI coding agents, and, it's a place where there's so much promise, but also so much frustration. I mean, if you're building software, you've probably felt this. You try to hand off a task to an AI agent, something like, hey, implement feature X across these 5 files.
Right.
You send the query, and then you just wait. It could be 5, 10, even 20 minutes.
And you have no idea if the result is even going to be usable.
Exactly. So you context switch, you start checking your email, or you go back to writing the code yourself.
It's that feeling. Researchers have actually given it a name. They call it the semi-async valley of death.
It's the perfect description. The agent is, it's too smart to just ignore completely, but it's way too slow to be a daily tool.
Yeah.
It feels like using really bad airplane Wi-Fi.
Yeah, it technically works, but it's just making you angry.
So our mission for this deep dive is to break down how one company, Cursor, really took on this trade-off. They already had a popular IDE, but they realized the only way to solve this speed problem was to build their own model.
Specialized agent model, yeah, called Cursor Composer. And it was engineered from the very beginning to be both fast and smart.
And that's the perfect way to frame it.
We've pieced this together from some really detailed talks from Cursor's own engineering and research teams. And their goal wasn't just, a small improvement. It was to completely get rid of that airplane Wi-Fi feeling.
To make something that feels almost synchronous.
Exactly. Something that actually improves productivity.
Yeah.
And they did something pretty remarkable. The key nugget we're going to unpack here is this one metric.
Okay.
Composer is measured to be 4 times more efficient at generating tokens than other models at a similar level of intelligence.
Wow.
And that isn't just a small gain. It's the difference between a tool you put up with and one you actually rely on every single day.
4 times is staggering. In this field, every percentage point is a huge battle. So, okay, let's unpack this. Before we get into the nuts and bolts of the model, why did they even go down this road?
It was all about speed.
Cursor was an IDE company. Why get into the brutal, super competitive model building game?
Well, it was totally driven by that user need for speed. They'd already built their own smaller models, like one called Tab for autocomplete.
Right, which has to be instant.
It has to be instant. If it's not, it breaks your flow. And when they tried plugging in these big, powerful, but slow agents, they just kept hitting that latency wall. They realized the only path forward was to control the entire stack.
The model, the training, everything.
Everything. So they had the ambition, but it wasn't a straight line. The early prototypes. That's where they learned a really tough lesson about what smart enough actually means.
Ah, yes. The wonderfully named cheetah slug.
The cheetah slug. It was fast. That was the cheetah part. But it was a slug when it came to intelligence. And the user feedback was, it was brutal, but it was crystal clear.
What'd they say?
Basically, speed is great, but if the agent can't understand my code base, if it introduces bugs, if it's just not smart enough, it's useless.
It can't be a daily driver.
Not at all.
Yeah.
So that forced this fundamental pivot. They set up a really strict internal benchmark. They said the goal is to build a model that our own engineers will use every day to build Cursor itself.
That's a high bar.
It's the highest bar. And it forced them to focus on what actually works in the real world, not just some abstract score.
So to hit that bar, what were the key technical changes?
It really came down to 2 major architectural shifts. First, giving the agent the ability to call multiple tools at the same time in parallel. And second, integrating their own semantic search tool really, really deeply.
Okay, here's where it gets really interesting for me, because that parallel tool calling, that's what kills the semi-async valley problem, right?
It's the direct solution.
So if you're a developer using it, what does that feel like in practice?
It feels like the agent isn't just waiting around. A typical agent, a serial agent, it reads your query, then it decides to say, read file A. It waits. Then it runs a command. It waits again.
And you lose your focus.
You've completely lost it. With Composer, it reads the query and immediately fires off several actions at once. It might be reading 5 different files, running a lint check, and doing a semantic search, all concurrently.
So it keeps you in the flow.
That's the whole point. It minimizes that cognitive friction. It feels less like a slow remote assistant and more like another pair of hands working right there with you.
And that speed is all unlocked by its toolkit and, I guess, how it's trained to use it. So can you walk us through what's in that toolkit?
Sure. It has about 10 tools total, but there are 5 that are really the core of what it does as a coding agent.
Okay.
The ability to read files, obviously, to edit files, to search the codebase using natural language, not just keywords,
That's huge.
It is. Then looking at lints, so static code analysis errors, and critically, the ability to run terminal or shell commands.
To test things, install packages.
Exactly, to interact with the environment.
And the big breakthrough here is the autonomy. The model itself decides, based on my request, should I run these one by one, or should I just hit a bunch of them at the same time?
Right, and that's what delivers the speed.
So how do you teach a model to make those kinds of high-level concurrent decisions? This is where reinforcement learning, or RL, comes in, but
Yeah.
that seems incredibly risky.
It was a massive calculated risk.
RL is famously hard, it's expensive, it's unstable.
Yeah.
Why go that route?
Because they found that just fine-tuning wasn't enough. It couldn't teach the model this kind of proactive, efficient behavior. They needed a system that would reward good outcomes, not just, mimicking answers.
And that's what RL does.
That's what RL is built for.
Yeah.
And their whole philosophy was to make the training setup an exact mirror of the production environment. They were essentially running real-world queries during training.
Through these rollouts.
Millions of them. And you can think of a rollout as just one attempt to solve the problem. In one rollout, the model might, say, read a file and then try to edit it.
Okay.
But in the next 5 rollouts, from the exact same starting point, it might do something totally different. It might do a deep code-based search first, run a command, and then try the edit.
And then you score the results.
You score everything based on correctness, efficiency, speed, and you update the model's parameters based on which path, which decisions led to a better outcome.
It's an elegant idea, but I imagine that's where the theory just slams into the wall of infrastructure.
That's exactly what happened. The team realized that 3 of their biggest machine learning challenges were actually infrastructure problems in disguise.
And this is the core of why it worked.
It's everything. You can't separate the model from the environment it lives in.
So let's break down those 3 challenges. What was the first one?
Okay, first, they were training a huge mixture of experts model and MOE model.
Which is great for speed in theory.
Right, because it routes a request to a small, specialized expert part of the model. But that means your training has to be incredibly fast to match the speed of inference. If training is even a little bit slow, the whole thing falls apart in production.
So the training has to be as fast as the real thing. Makes sense. What was hurdle number 2?
The rollouts themselves, the complex and variable rollouts, like we said, these can involve millions of tokens, hundreds of tool calls.
Some are super fast, like reading a file.
And some are incredibly slow, like installing a huge library. They finish at completely different times, which leads to a massive amount of wasted compute.
You got GPUs just sitting idle, waiting.
Exactly. Thousands of them, which makes scaling RL insanely expensive.
A resource allocation nightmare.
Okay.
And the third problem?
Consistency. To really mirror production, the agent in training needs to get information file contents, error messages, search results in the exact same format as the live version.
But training isn't like production.
Not at all. Training is bursty. It happens in these huge temporary blocks. Production is a steady, continuous stream of user requests. Bridging that gap is a huge challenge.
Okay, so we have the problems. How did the infrastructure team start chipping away at them?
On every level. Let's start with training, speed, and that MOE requirement. The research team actually developed a library of custom kernels.
Wait, custom kernels? That sounds like a massive engineering effort. What does that even mean?
So think of it like this. A GPU usually runs on general-purpose software. These custom kernels are like tailor-made instructions, hyper-optimized for one specific task on that specific hardware.
For the MOE layer.
For the math and the MOE layer. And by doing this, they squeezed out just incredible efficiency. The specific nugget here is a 3.5 times speed up on NVIDIA Blackwell chips, just for that one layer.
Wow. That alone solves the speed matching problem.
It's pure engineering unlocking the ML.
So what about the variable rollouts? The wasted compute time?
For that, they built really sophisticated load balancing right into their inference server. It dynamically shifts work around. So if one process gets stuck on a long install,
the server just gives its other work to an idle process.
Instantly. It keeps the whole cluster running at max efficiency, no wasted time.
But the really clever bit, the big aha moment, was how they solved the consistency problem, the co-design approach.
This was the genius move. They co-designed the RL training pipeline to run on the exact same system as their production cloud agents product.
So they're training the model in the wild, basically.
They're training it in secure, sandboxed cloud VMs that are identical to the production environment. By doing that, they didn't have to fake anything. They got a perfect one-to-one match between training and inference.
And that solved the consistency problem and let the RL training actually work.
Let it stabilize and thrive.
That tight coupling brings us back to one of those critical tools, semantic search. The model didn't just get faster, it got smarter about using its tools.
Yeah, semantic search is the key. It lets the agent use natural language, like find where we handled database timeouts to find the right file instantly.
No more guessing.
No more guessing. And what was fascinating in their research was that semantic search helped every model they tested, but it was like supercharged for Composer.
Why?
Because Composer was trained in the exact environment where that tool lives. The RL process didn't just teach it to use the tool, it taught it to be a power user of its own tool.
It knew exactly when and how to use it for the best result.
Precisely.
So it's not just about raw speed, it's about improved behavior.
100%.
Yeah.
The RL training led to better decision-making. Initially, the model would make too many speculative edits. It was too quick to jump in and change code.
And probably introduce bugs.
Often. But as training went on, it learned restraint. It learned to be more efficient, to search more, to read more files before it tried to make an edit, which made the final result cleaner, faster, and more correct.
And that combination of smarter behavior and pure speed is what finally gets the developer out of that semi-async valley of death.
It restores that feeling of synchronous in-the-loop coding.
Right. And users are now creating these really interesting workflows with it.
Yeah, we're seeing them use the biggest, slowest, most intelligent models out there to write the high-level plan, the architecture,
The big brain work.
the big brain work. Then they hand that plan to Composer to do the fast, efficient work of actually building, implementing, and debugging it. It's a perfect pairing.
Maximum intelligence for planning, maximum speed for execution. That's a powerful combination. Okay, so let's wrap this up with the key takeaways for you, the learner.
I think the first one is that this project really proves that RL can work incredibly well for these highly specialized models, like for coding,
But with a huge caveat.
with the huge caveat that you have to have the environment match data and, critically, the infrastructure to back it up.
And that connects to the bigger picture, right? The biggest hurdles in ML right now are often infrastructure problems.
They're totally inseparable. You have to solve the infrastructure, the custom kernels, the load balancing to unlock the ML potential.
And finally, there's this compounding effect. When your own team uses a faster tool like this to build that tool, they can just iterate faster.
They can try more ideas, ship products quicker. It becomes a self-improving loop for the whole organization.
So we've seen this co-design of the infrastructure and the training lead to a model that became a power user of its own proprietary tools. That leads to our final thought. Consider how training models to use specialized proprietary tools inside environments that perfectly mirror production. That could be the next huge frontier.
Whether that environment is a financial modeling system or a CAD program or even a physical factory floor.
Building indispensable AI agents that are experts not just in a domain, but in a specific set of tools. Something for you to mull over.
That's it for this deep dive. We hope you enjoyed the shortcut to being well informed.
We'll catch you next time.